And 5, 4, 3, 2, 1.
Hey, good evening, everybody. Welcome, welcome. My name is Lars Torres. I serve as Executive Director of the Artisans Asylum, and I'm thrilled to welcome you to our first Artisans Residency. The whole idea here is that we've got about 500 square feet in a warehouse in Lower Alston, and our goal is to make some of that space available for artists in this time of COVID to break out of those bedrooms, small rooms, go big. And I'm thrilled that we have James D'Alessandro and Jason Hasko as our first artist in residence. As they're going to show you tonight, they've gone big, and it's really exciting. So without further ado, I am going to hand it off to the two guys. Both of them work in the architecture field. By night, they're building an artistic practice. I'm thrilled to share with you tonight CORALYTE. Take it away, guys.
All right, I think we're hooked in. Hey, I'm James D'Alessandro.
And I'm Jason Hasko.
And we're Emergent Design, here to present our Artist in Residency project. After 30 days, it's CORALYTE. We have a presentation we're going to jump right into. Great.
We're a multidisciplinary design technology company building computational solutions for your complex design goals.
And our project CORALYTE is right behind us. The inspiration from the name comes from fossils of corals. When a coral dies, it leaves behind a skeleton. And as you can see here, you look at the branching structure of this coral skeleton, and you can see these little polyps that form all over it. It's sort of a fractal structure where branches branch off branches. And that brings us to when we were thinking about the form, we wanted to do something from coral branching and other things in nature, such as minimal surfaces. Minimal surfaces are surfaces that form in soap films and bubble froths and all over nature because it's the most efficient way to minimize the surface area of a given volume. And it's very strong tensilely. So when we began our project, we wanted to map out the space in 3D. So we took a lot of measurements and we put in our linear skeleton of what we desired to be our final form. And you can see in the next slide, we're going to have our form finding video that's going to play for you right now. So this is sort of the process of how our form was generated. We generated the line work, and that then forms this tensile structure through a physical simulation to relax the mesh. And then we remeshed it into triangular strips, so that we can then fabricate them. I'm going to restart the video and play it again for anyone who wanted to see that a second time. You can see how it goes from the initial form to a optimized form through the tensile relaxation process.
So then we started looking at the fabrication process, considering how we could build such a complex form. With access to the Artisans Asylum, we had a couple of laser cutters, and we were very familiar with a paper-like material called Bristol board. It's pretty strong, and we knew we could laser cut it really quickly. So then we jumped into a prototyping scale, something about the size of a shoebox. We broke down this original minimal surface form into strips that could then be flattened into laser cut parts.
So you can see here, we have a system of binder clips and tabs on each of these triangular faceted strips. So each one joins up with its perfectly matched neighbor. And we have a system here where we were referencing the 3D model to build this initial prototype that's only about 2 feet tall. And we knew that that wouldn't scale. We didn't want to have to reference the 3D model constantly. So we knew we had to do some sort of inbuilt assembly and fabrication information onto the model itself. So we didn't have to constantly reference the 3D model when actually assembling the final scale assembly. And here we moved into, after that first prototype that was at a small scale, we moved into a 1-to-1 scale prototype, and we added the second layer to the design, which was instead of just plain paper strips, we also had triangular holes with these things that we called petals sticking out of them. And you can see here in the full scale mock-up of one chunk of the final form, we have strips that have no holes, strips that have some holes, and strips that are fully comprised of holes. And you see there's different sized petals. And each of those is just friction fit right into the paper.
And at this scale, testing this material assembly one-to-one, we learned a lot. First of all, the diameter of our surface here was a little too large, and also the base. You can notice we had to tape the tabs onto the table. The base needed a rigid frame to attach to, so we designed a plywood anchoring system right at that flat planar edge.
And jumping into zooming in on these strips, each strip is comprised of multiple triangles, not always 4, maybe some are 3 or 5. And at the edges of each strip, as you can see on the right side of the screen, on the tabs, there's the assembly information. So breaking it down, in the boxed letters, you see N, 10, D. N refers to the subassembly that is comprised of numerous strips. 10 is the name of that strip, so each tab on that will have the number 10. And then D is the identifier for the tab. And you can see next to that, it says N6D, and that's the one that's across from it on the table there. So you can see that N10D pairs perfectly with N6D. And in this way, by putting the assembly and information right onto the tabs instead of on the faces of the triangles, we were able to hide all that information from the final viewing, but also allow people who weren't intimately in the process of building and designing this thing, they were able to fully assemble it without any prior knowledge of the 3D model or how even the final form would look.
And yeah, many of them had no idea what it looked like and had no concept of this building assembly in the first place. They kind of jumped on board and were able to work through this technique easily.
It requires no instructions, only a set of rules to follow to build this thing. So you can see that we have 20 sub-assemblies, each colored differently with a text tag. You see we have A through T. And these sub-assemblies were sized so that we could reach our arms inside and clip the binder clips to connect each subassembly to the next one. So for example, in the bottom right, you have M and then N. Each one is only maximum of 3 feet long between each opening so that you can reach, the average sized arm in there to clip them together for actually assembling the thing.
And in some cases, a little bit larger of an arm from our good friend.
Yeah. And in each of those subassemblies, the whole thing is cut into strips. So it's not just each face is its own thing. You have each strip. And then each of those strips is still within its subassembly. So we have sort of 2 layers of data. We have the subassemblies, numerous within each subassembly, and those are numerous within the whole form itself.
Mm-hmm. And at this stage in the digital world and planning, we knew that we could build all these subassemblies individually on tabletops and on the floor, and then bring each subassembly in and attach them to the walls, to the ceiling to bring the whole final form together.
And remember that each of these is 1 strip of paper.
So in total, we've got some stats for you. We used 8 pads of Bristol board paper, which is 146 sheets. And here you can really see the benefit of making strips. Instead of having 3,005 parts representing each face, we had about half of that, turning them into strips. And we had almost infinite binder clips, and there's no glue or tape involved in this assembly.
This whole thing could come back apart and lay flat again. And why don't you tell them about the petals?
So the petals, instead, each mesh face is unique. We didn't want to have a bunch of unique petals that we had to match to individual faces. So we broke down 3 typologies, meaning they were the exact same part that we just had to cut multiple times, as you can see with the numbers there. That was about 15 sheets of material, and we used no adhesive or clipping system to attach those. You'll see in some photos later, we designed a tab system that friction fit into the holes on the final mesh. Here is a 3D example of the 3 different types. Pink is in small, blue is in medium, and yellow is in the largest form.
And you can see how they fade from the edges to the center, and it's a gradual distribution of those on the form.
And so again, emphasizing these typologies, we only had to cut the same 3 parts multiple times in a row. And in order to do that, the triangle shape had to be equilateral, even though the mesh faces might be a different shaped triangle. And you can see that highlighted in pink there.
So this is a sort of a typical example of fabrication result from the laser cutter. We used a software called OpenNest to nest each of these for layout for manufacturing to sort of not waste as much paper as we could. We wanted to sustain, keep all the paper as good as we could and not waste paper. So we have these tabs and strips, and they sort of all fit into as few sheets as possible. And it ended up being around 50 hours of laser cutting throughout all of our prototyping and final assembly and cutting.
Yeah, and that's with 2 laser cutters, most of the time running at once.
Yeah. And here this is when we started building a few nights ago only. And we had, you see, we started building each subassembly. On the left there, you see 3 of them just scattered about off to the side after we'd done building them. So it was easier to build each subassembly rather than try to attach strips to the whole form. We built all 20, and then we started attaching each 20 to the whole form.
Yeah. And on the right, you can see we started at the highest point, at the ceiling, anchoring to some of the I-beams here in the space. And you can see how the next subassembly is coming into place, and we're reaching our arms up through to clip that onto the previous assembly.
This is a good image on the right here where you can get a sense for the size of each subassembly. It is about the length of one arm. So it was sometimes you really had to get your shoulder in there and really get in there to clip the next thing to it. And if you look in the left here, you can really get an example of just how many binder clips we had to use. Each tab requires 1 clip and its neighbor. They clip together. And if you also look, you can notice the small tabs on the pink petals, and those just fold in and grab on the interior of the face for each of the ones that have a triangular hole.
And on the right, you can see another process photo. At this point, we had the top secured and both wall anchors secured, about to build the 2 bottom components out. And yeah, in total, the whole assembly process took about 2 days. We had 64 hours the first day to build all the sub-assemblies, which is folding each strip and connecting those into their sub-assemblies. The next day was 80 hours, and that was actually building the whole structure and inserting the petals.
Yeah, if you look here, you can really get a sense for how it spans across the space. We wanted it to be site-specific, so you could walk under the arm that you see on the right side of the left picture, and then walk through behind it along that wall and out towards the camera in that left photo there. And it also gives you a nice sense of distribution of the petals on the overall form. It wasn't random. That was controlled by a tractor curve that distributed those petals on the form and dictated which faces got holes and what size of those holes they were.
Here you can see in the core from behind the final form, the density of petals being most intense in the core, giving for a really unique and more personal experience. This difference in sense of scale and space was an important experience for us when designing this from the beginning. Here again, you can see that sense of scale. As you enter from the right, you can look up through these holes and experience a more higher density of these petals being at a smaller scale, more human scale, and coming back around and revealing some more of the process. And one thing I want to point out on the right side of the photo against the wall, you can see there's a gap. This is where we had the plywood sheet where the paper is clipped onto the plywood. And then we had some blocking with a aluminum wall cleat, which allowed for some tolerance both left and right and up and down. This was very important for the final assembly process. Again, here, the final form from another point of view, you can see how these holes kind of change the shape and form and scale of the final installation.
Yeah, and if you look here, you see the 2 anchors on the walls are sort of floating off it. And I just want to touch back on when Jason was talking about how it allowed us that tolerance with those wall cleats. As we were building this far right arm, that was extremely important because the whole form wanted to tug to the left, and allowing it to have some leeway by sliding those anchors left and right basically made or break this thing while we assembled it and allowed us to connect the forms that were giving us trouble and then reattach it to the wall.
Yep. And you'll notice here at this point, you can even see in the shadow on the floor of the left foot, it is actually not touching the ground. So our only 3 anchor points are the ceiling, the 2 walls, and the 2 legs on the feet are not touching the ground at all.
Yeah, those aren't structural. Those are just to give a sense of tension and connect it to the ground visually. But it's all being supported through tension hanging from those 3 walls and ceiling points.
Yeah. All right. And now we're going to segue to a walking video. Please bear with us. The camera might be a little bit shaky. So if that makes you uncomfortable, please bear with us.
All right. All right, if everyone can see here, I've got the camera moving around this form, and this will give you a sense of scale. You know, I'm walking right around, you can see Jason all the way over there, walking underneath that left arm, looking at these petals. This is the best spot in the house, where you walk under, and you can look all throughout with me. And I'm laying down on the floor right now, and you can really get a sense for how large this thing really is. I think this right side, the ceiling branch is 12 feet in the air, and both of these are, the wall ones are 8 feet up. So this thing is pretty massive. We haven't done a weight estimation on it, but I think it's at least over 50 pounds.
Safe to say.
Safe to say. Here, I'll give a zoom in on one of these petals so you can kind of see how it reveals the form inside. Maybe if you're a bit lucky, it'll focus on the interior there, and you can see the binder clips and the system that holds the whole thing together without any glue, adhesive, or tape. Awesome.
So now we're going to be segueing into a Q&A session. So please feel free to post your questions in the chat, and we will address those
As they come in. Here, let's see. We've got some already. And if there's any on YouTube, maybe we could have someone tell us. Q&A. What software pipeline did you use to generate the design? That's from Griffin Van Home. That's a great, Griffin Van Horn, sorry. That's a great question. We used a combination of Grasshopper, which is a plugin for Rhinoceros, which is a CAD program that we're both really familiar with. It uses NURB surfacing and meshes. We used Grasshopper, which is the visual scripting component, and a combination of C# custom written scripts to generate this form, and also especially to take that parallel data from the edge information and put those onto the tabs so that we could then, you know, pair each tab to each other.
Yep. The only other software involved was just the laser cutting software. We were able to export directly from Rhino to the laser cutters.
Yeah, it was a pretty all-in-one solution with the custom scripts in Grasshopper and Rhino to directly to the laser cutter. So that was great. Do we have the YouTube live?
No. If we were to do it again, what would we do differently? What future directions would you like to go in with future projects? That's a great question, Griffin. Thank you very much. I guess some of the things we would do differently, I think certainly I can get started with. We would calculate the weight, I think, is the first thing. We didn't really have an understanding of how much tension was going to be on some of these anchor points. And we designed them to withstand hundreds of pounds. But granted, we still had some difficulty in stretching and pulling towards some of the wall anchors, especially as we were in this core area. Some of those sections became really big and heavy, and luckily we had enough hands that we could pull it taut while assembling the next piece. But without all that labor, we would have needed a complex rigging system or something like that. So I think in the future, something that maybe comes a little bit more from the top down, simulating some gravity, could definitely help us in the future.
Yeah, and I think as far as future directions we'd like to go with future projects, I really enjoyed doing this installation, and I think it would be great to do something a little bit more permanent. Maybe something with aluminum sheeting or steel sheeting or wood. This is paper and it's really nice, but it does have to come down fairly soon.
Yeah.
So I think a more permanent installation and possibly something on the exterior instead of interior would also be really cool. Something that can withstand all the elements.
Yeah, I think it's a system that could be applied to many different scales. So we could make pavilions just for parks and even lobby areas. Could be an interior ceiling system, but it could even be the exterior of a building that moves and flows across a building with window apertures and all the fixings. Great question.
Yeah, that's a good question. Yeah,
Us
top rivets and aluminum, that would be great.
Rivets would definitely be the way to go.
I think we have the next question from YouTube, is that right?
Hi, I'm Carolina. I'm doing your outreach fellowship here at ARTISANSxRESIDENCY in Austin. So we do have a couple of questions here on our YouTube live, so we'll go ahead and get those questions up for you guys in a second. Okay, so our first question is, do the binder clips have enough weight to them to cause any sagging / tensions across the body of the form?
Do the binder clips have any what?
So do the binder clips have enough weight to them to cause any sagging / tensions across the body of the form?
You'd actually be surprised. Each binder clip is quite light, although there are 2,000 of them. And honestly, the thing that adds the most weight is just the amount of paper. The Bristol board is not too thick. It's about the same thickness as cardstock, but that's plenty strong to withstand the weight of the binder clips. And given the fact that they're fairly equally distributed throughout the interior of the form, that weight isn't localized to any one pain point, so we don't really experience sagging in any part due to the binder clips. I would say most of the sagging is built into the tensile form that was generated, and any unwanted sagging is really just due to localized areas where like maybe a binder clip isn't fully affixed to the center of the tab and it's due to the paper.
Yeah, some manual error maybe could affect the final tension and point modes.
And generally when we fold these things together and assemble them, the system is really good because they can't go together any way except for the way that the form is designed to go. So as you put it together, it sort of lays flat. And as you fold it up, it assumes the form that it was designed for. So you can't really have like an unwanted kink. Otherwise, you really have a big problem.
Awesome. So let's go on to our next question. You guys ready?
Yep.
Okay, awesome. So the next question is, could this be made in a more solid material, or would this only work with Bristol?
Great question. I think we kind of addressed that a little bit with Griffin's question. Any other kind of sheet material would work great, either solid aluminum or a composite sheet, plastic even. We could certainly use CNC to mill some of these other types of materials. And then you could get a V-groove drill bit, if you're familiar with CNC, to get some of those angles and those pivot points. But the laser cutter worked great with the scale of the material we were working with.
For an analogous process for a stiffer material, you could use a plasma cutter or water jet to cut aluminum sheeting, and that would fold up much the same. There would only have to be some considerations for the thickness of the material, which were mostly negligible with the paper, although aluminum would be a little bit thicker, but completely possible for the same type of construction system.
Okay, our third question is, what made you pick the colors for the piece?
Okay, the question was what colors? Why did we pick the colors? We pretty much had white because Bristol is white and not going to spend a lot of money to go get some custom colored Bristol.
Yeah.
That would be really expensive.
Yeah, and I think the pink, we explored a couple colors at the beginning in our digital model, but the pink really spoke to us in some of the life cycles of coral. There's some really fluorescent pinks in coral life, but also the space we're in, are some really beautiful pink lanterns that you guys can't see right now. And they kind of accent the space really well. Those kind of look like jellyfish while we've got this coral piece behind us.
Do we have any other questions from YouTube or no?
So the next question we have is, did you have to make any compromises due to the lack of time?
Okay, the question was, do we have any compromises due to the lack of time? I think we had some more extravagant visions for the second layer of the design, these petals, when we were coming up with just the whole ideas when we were still in the prototyping phase. We had some grandiose ideas about like ribbon type material sort of screaming about the whole thing. And then it sort of got scaled back to, well, we can cut triangular holes and pop in these little folded guys.
Yeah, we even considered, again, you're emphasizing another layer of paper or design of this. We even considered laser etching a pattern onto the paper that didn't align with the grid of the mesh faces, just to give it a more organic look. But with that time constraint, we really had to simplify the system as much as possible while still making it buildable.
And the advantage of this computational workflow that we described, there's a lot of work up front to set up the system, but then any changes that happen during the designing phase, when you run across something through prototyping, it makes it extremely easy to then generate a new form that follows those rules.
Yeah, we actually even ran calculations while we were nearing the final form concept, and we tested nesting out how many sheets of paper we'd have. And some adjustments we made, we realized were bringing us up to 20 sheets of paper, which is way too much, both time and money-wise. So we are constantly using our software to cross-reference material estimates and cost and time analysis.
And speaking of those material estimates, back in that form finding video, when it became triangulated, we ran some multi-objective optimization processes on it with particle swarm optimization software to minimize the number of strips and maximize the average length of each strip so that we didn't have any singular face strips. At least they would be 2 faces, and they would be the least amount of total strips, because that cuts down on assembly time and material usage.
Yeah. So in layman's terms, we are trying to make the most amount of faces per strip. So we had, in total, we had to laser cut less parts.
Exactly.
And there's less labor involved.
Awesome. This one's a really funny question. You guys ready?
Yeah, all right,
Sure.
funny question.
How tall is the tallest person who helped you out on this project?
We could have asked that question. That was Kevin Fitzgerald, who we
Yeah.
could not have done this project without.
6'4", and his wingspan is 7 foot.
So
That was key.
and actually at points, we really, really utilized his whole wingspan.
Yeah.
He was shoulder deep at a few points.
Yeah, he probably deserves a raise. But,
Yeah.
Sure.
Yeah.
So what you didn't see in our presentation, we're gonna take a pause from the questions for a moment while you guys come up with some more. This plywood base, we didn't have any pictures of in the presentation. We laser cut it, and there are holes so we can still attach the binder clip to each face. We also made some holes that are a little bit larger so you can still reach a limb or two in there to finish fastening the last couple parts on. So this plywood base exists both at the ceiling at an angle like this with some hardware, and then it's also on the walls like that. And there's a wall cleat fastened to the plywood there.
And here's an example of a extra strip we had, or one from the prototyping. And you can see that each edge is perforated. And we did that because scoring, where you don't cut through the material all the way, is only a one-directional folding technique. And some of these fold out, although most of them fold in. We didn't have any guarantee of which did what, so we went with the perforation. It's also easier because then you don't have to have a separate setting for the laser to cut halfway through the material. You can just have one setting for a full cut, and you decide where it cuts only on the perforations. If you look inside here, we can get a look at the back side of the petals and how they just pop right in and fit. And you can easily take it out, but as long as no force acts on it, it's not going anywhere.
Sure. So again, on one of these parts, we can emphasize this code a little bit more. Again, the circled ID number is the identifying this exact tab. And so you'll notice a letter N, which stands for the subassembly, and the numbers in the middle stand for this part. And you'll see on every single one of these tabs, it's circling N2, 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 and so on. And then the last lowercase number is the unique tab. So we've got C here, while we have an A and backwards, an A over here. And then the ID that's next to it, that's not circled, actually belongs to its neighbor, the tab that this clips onto. So as we're assembling, we could pick up any part and see what strip it attached to, find that strip, line up the two tabs, clip it together, and then keep moving forward with that process.
And in this way, someone who had absolutely no experience with the 3D model could build this entire thing.
Yep. All you
Without
need to
looking
do
at
is pick up the part, look at the ID, pick up the next part, clip it.
Yep. I don't know if there's any other questions.
We do have a lot more questions.
Oh, we do have a lot more questions.
Nice.
So our next question is, I know you took this form from coral, but what other nature-inspired ideas could you apply to make more art or industrial uses? This is from Diane Rippey.
That's my mom. Okay.
Shout out to the mom.
All right. Diane Grippy asks what other nature-inspired forms we could use to create art and design like this. There's infinite variations. I mean, branching algorithms that you see in tree and root growth of plants, or cellular division algorithms such as mitosis, or spatial distribution algorithms such as like Voronoi cells and other grid systems. Mushrooms, fungi, mycology grows in really interesting branching ways, especially things like slime mold, which they use to create shortest path connections between like cities to plan out highways or even subway systems. It's a single cellular organism that's smarter than a computer in those specific applications. And that sort of thing is really interesting in the field of computational design, because those algorithms that you observe in nature can be used in different contexts through applications of these algorithms that are developed to mimic those. Yeah. So I mean, there's practically infinite variations and uses for algorithms that you see in nature to apply to design.
Yeah, and all those methods of constructing and all those embedded algorithms that you find in nature have become quite efficient. And so if we can start to apply them into the built environment and physical objects, then we can optimize that, we can utilize that efficiency as well.
For example, this is based off minimal surface algorithms. And so if we, the reason we did that was to minimize the surface area, which ultimately minimizes the amount of paper we're going to have to use to create this thing. Yeah. So by starting off with the minimal surface algorithm as the basis for our form generation, we were able to ensure, you know, in the end, maybe we don't have to use as much paper as some other approach that we might take.
And we didn't have to run a separate physics test and calculate the weight. The reason we didn't do that, which we should have with more time, but the reason we were confident without it is because by nature, minimal surfaces have some structural integrity to them. So we knew that this final form was going to stand up and hold itself together.
Mm-hmm. Any given point on the thing is ideally distributed in tension. Yeah.
Okay, so we have 2 more questions.
All right.
Ready?
Great.
Okay. So we have one from Peter.
Come on.
Can you disassemble it and replace the parts easily?
Yeah. It's just binder clips, no glue. So,
well, he's asking about a repair.
Okay.
We could disassemble the whole thing by starting from the feet or any of the anchor points, and we can flat pack the whole thing for another installation location. But I know Peter, and he's asking about repairing. If we had damage to just one of these parts, can we access it and replace it easily? Unfortunately, we can't. We would have to come up with a different solution. We could certainly get the part out, but we couldn't use the same technique of binder clipping. We'd have to use some kind of adhesive, perfectly inserting the part into there and hoping the tabs stick to some glue on the tabs.
Either that, or we'd have to backtrack out and remove each subassembly to allow access to that area, and then build it back out.
Build it again.
Which is totally possible, but it would be a lot more time consuming than what Jason just proposed.
Yeah, absolutely.
Yeah.
Great question, Peter.
All right.
Okay, awesome. Next question is from Wesley Alvarado. What other materials would you like to explore with the next iteration?
What other materials would we like to explore in the next iteration?
Yeah, so I mean, we named some of the sheet materials we might try next time, like aluminum or composite. But I think additionally, we're also pretty interested in this second layer of material that we're adding to it. So I think next time we might explore some transparent plastics that can still bend, but they would create a more interesting light experience.
And another thing that kind of ties into the minimal surface thing is some sort of stretchy fabric or textile material. That would also be an interesting way to mimic the form of minimal surfaces. All you have to do is then know the exact flat cut pattern and then sew it together or stitch it together. And you could generate some similar forms that would be stretchy and tensile like this, although not faceted like the paper. Right. So that's another interesting thing. Maybe some textile or stretchy fabric would be an interesting approach.
Yeah, and many of these other types of algorithms and forms can certainly be explored with 3D printing as well, which is an avenue that we're going to be exploring in the future.
Yeah, so if you think back to the first prototype we showed where we were building it in front of the computer, the tabs were on the outside. So something we floated in the very beginning when we were just coming up with ideas is to have the tabs instead of on the inside, but on the outside. And then those could serve as a attachment point for like some 3D printed clips to then attach a second layer on top of. So perhaps for the next version of this, we do an inside-out version where we can then use those tabs sticking out to attach, I don't know.
Yeah, you could make custom connection points that maybe have ball joints or specific angles to a more custom design. Really utilize that manufacturing process to batch automate unique parts to these kinds of complex forms.
Mm-hmm. Was that the last question on YouTube?
Yes, that's
okay.
the last question. You have a lot of friends saying hello.
We have a few.
Hey guys.
We have a few questions in the Zoom, so let's read those. Griffin Van Horn says, "I'm excited to see what direction development goes in. How could I get involved to help with assembly and future projects?" If you are in the Boston area, which is where we're located, you could visit our website, www.emergent.design, and send us an email and reach out, because we had to get the help of like 8 of our friends to build this thing. So it would be great to get some extra help on the next one. That'd be awesome.
Yep. And as we work up in scale, we'll need more installers, art handlers, things of that nature. And if also any of you have outlets to spaces that could use some beautiful art, please contact us on our website as well.
Yeah, definitely. Dick Rubenstein says, "Would you want a more permanent material to be laser cuttable? Metal would be quite different, though you could use a plasma CNC. I know there's a plasma CNC at the Artisan Asylum, so that maybe would be the next sort of thing. I think this is very easily directly translatable into a sheet metal that would be able to be cut on a plasma table. So that sort of is the obvious thing. Although, you know, this isn't the only type of thing we do. We would love to work with CNCing on 5-axis machines for wood and metal, and creating all sorts of designs with that.
Yeah,
fabrication process.
We could make these panels individual faces out of wood as well, and CNCing each edge vertice to a specific degree with a 5-axis mill to merge to its partner at that perfect angle that they're connected at.
Yeah, custom miters. Yeah, so I mean, we're not obsessed with the laser cutter. It's just what we had access to and knew we could deliver in 30 days using that as our fabrication system.
Yeah, great point.
We actually have one more question for you on YouTube.
Great.
Cool.
From Wesley again.
Okay.
Will you guys explore kinetic features with your next iteration?
That's a good question.
It would be very cool to have some part that moves. Perhaps not out of paper though. Might be easier to have it anchored to a more stable material if we have some moving parts.
Yeah, certainly. And working with servo motors and systems like that, Arduinos, we could certainly be embedding moving parts into different parts of these systems. They could have a logic that applies both externally to the pedal design that we have here, and it could be embedded into these sub-assemblies with simple connections, wired connections in between that. We certainly have explored some of those ideas theoretically, but we'd be very happy to team up with a team of experienced people who work with Arduinos and motors more often. Good question, Wes. Thanks.
All right, well, I'm not sure if we have any other questions. So if you do have any, shoot them off right now, because we're still hanging around. We've got the Zoom Q&A open, and we've got the...
Sure, Lars has got a question for us.
Yeah. So I got a question, guys. It's been really fun to experience this process with you. We've been building out this space at the same time as you've been using it. Thinking a little bit from the perspective of how Artisans Asylum can continue to advance its mission of supporting artists, what feedback would you have for us? How could we have improved upon this process for you? What else did you need? What were you not able to do that you would have liked to have done?
Well, here, let me unmute Spotlight again. Jason wasn't a member of the Artisan Asylum, so he couldn't run the laser cutters. And I mean, it would have been nice if we could have like expedited the process to get him on the laser cutters, like trained, so that we could instantly get in there.
So you weren't the only guy working at 4 a.m.
Well, he was there. I was there, but I was the one that had to do the actual laser cutting because he wasn't trained on the machine. Another thing would be giving us parking passes to the thing. Maybe the rest got towed, but we didn't have any parking passes. We did park in the parking lot. We did have 24/7 access to the space, so I mean, it was totally easy to come in here or the Artisan Asylum to fabricate at any hour of the day, and that was great. I don't know.
I think, I mean, it's probably unrealistic, but something for us that challenged us was just getting up to that I-beam with the big ladder Some scaffolding would have been great, though I know you guys aren't necessarily planning for the size of an installation, but that would have been helpful for us personally.
Yeah. Overall, though, it was really, you guys facilitated it really well. I mean, we were able to come in here 24/7, go to the artisan 24/7, schedule fabrication. You know, I mean, the whole place being, to us, it was just really easy for us to ideate and sketch and get into the whole groove of things.
Yep.
Well, good. That's exciting. So what's next in terms of, what do you think could be an application that you would like to see this evolve into? What's the next sort of application for this beautiful, really organic and yet clearly highly geometric, highly technical form of installation art, if you will, if nothing else, architectural art? What's next? How would you like to see, if we had unlimited resources, what would we do with you next?
If we had unlimited resources, we could build a whole built environment on the interior of this space and have, you know, a permanent installation at the Artisan Asylum or something like that.
Yeah, you know, and Artisans Asylum moving to a new location here in Alston might be looking for some unique sculptures, both outdoor and indoor, to really access the space and create some more unique meeting spaces versus studio spaces. Some of these surfaces could span across some of that, and even could function as a canopy for an entry sequence, keep the rain off people's heads. I think there's plenty of permanent built opportunities for this kind of thing, but also even just for events, we could provide temporary coverings and wall surfaces to create a background for an event or photo shoot, things like that.
And sort of at the opposite end of the spectrum for that answer to that question, this sort of thing is easily translatable to like a kit for like someone to build in their own home. Yeah. So maybe you do in the future when people have access to 3D scanners, like people have access to paper printers today, perhaps someone could 3D scan their room, identify anchor points that they would like to place things on, and then using like an online tool, generate a form like this and order the strips to be sent to their house, where they just simply follow the easy assembly instructions and assemble it, a custom one of these in their house.
Yeah, that's a great point. I think we're really interested in distributed manufacturing, meaning have the same types of machines in more localized communities where you can make complex forms with simple assembly logics.
Yep.
So that anyone can have this kind of thing in their home or at their office, etc.
This sort of thing is extremely simple. I mean, a child could put this together.
Yeah.
Really, it's like Legos. All you have to do is put the tabs that match.
Easier than Legos.
It's sort of easier
right
than
where
Legos.
to put it.
It's a little harder than Legos.
Well, I like this idea of assembly logic, and it seems like, Jason, you know, your background in fabrication and I think facade design, I think making it easy to assemble is where a lot of the heavy lifting is, right? That organization. You did start with models. I remember early on you had some maquettes that kind of you then scaled from. And I could imagine that educational kits that help folks think about the organization of scaling up could be really helpful. You know, you start small and you learn to kind of connect the right dots, and then pretty soon you're off and running.
Exactly.
Okay.
Yeah, that's the exact kind of assembly logic, and that's the same way we ran it, and that's the same way anyone else could learn from this system. Is you start small in a prototype scale, somewhere where no one's going to get hurt. It's not going to cost you a lot of money if you fail, and when you fail, you learn even more, and you can work your way up to larger forms and more complex systems that can become more permanent.
A lot of people, when they have a laser cutter or access to one, will start with like very basic. You take a 3D form and slice it into layers, and then cut those out of like chipboard or something and pile them on top of each other with glue to create the 3D form. And that's really simple in both form generation and in assembly logic, whereas this is complex in form generation, but very simple in assembly logic, much the same as the stacking of the layers. So if people like us generate a software to create things like this, and you can order it online or something like that, the actual assembly process of it is just as simple as, you know, the most basic of laser cut projects, really.
Right, exactly. So, and that's a great point. It's about access to tools. And most people have a laser cutter within 10 miles of them, 50 miles of them, maybe out in other parts of the country. And so if there was just only a accessible software, maybe a web-based platform where somebody could generate this form themselves to the size and scope that they need, they can use those tools that they do have access to make these kinds of models for their own uses.
Yeah.
Well, one of the things that I'm excited about is as Artisans Asylum grows, right, we know we have to move from Somerville here into 2 buildings. In 2025, we want to secure a 3rd site, about 5,000 to 10,000 square feet, where we can really create what I would call experiential wonder, right? I know I've talked to you about Meow Wolf and some of these places, but really leverage artists like yourselves to build an environment, an immersive environment where young people, anyone, can experience kind of an aha and wonderment driven by artwork that we probably haven't experienced in 3D before because there's so much computational power behind it. I mean, other than our buildings, right? I mean, but this is really something different. So let's keep in touch. I look forward to embarking on this journey and seeing how this work can scale. Real quick, I know you've been supported by a team. Would you like to bring them forward and introduce them?
Yeah, we've got a couple members here today.
Come on, team.
Yeah, we have some of the people that helped us build this thing here, but the people who aren't here, I'd like to thank right off the bat. Nick Haskell, Jason's brother, we could not have done it without him. Kevin Fitzgerald, we could not have done it without him.
There's another camera here.
Nate Billman, could not have done it without him. We've got Valerie Schmerlo, Megan Johnson. We've got James Sand. He's taking a lot of photos, and he's been really integral to documenting the entire process. Is there anyone else I'm forgetting?
Yeah, Nate. My sister, Rebecca Haskell. And
we said Kevin. Kevin got a couple shout outs. Kevin got a couple shout outs. He's 6'4".
Yeah, and I guess I just emphasize my brother Nick has experience as an art installer, and he was really integral in kind of the whole planning process, planning and consulting on that side of things. So
Yes.
huge thanks to Nick.
We had 8 people here 2 nights in a row, sometimes till 2 a.m., sometimes even later, working just to get this built, and we could not have done it without them.
Yeah, and shout out to the moms and dads. We wouldn't be here without you.
Shout out to moms and dads in the YouTube chat. And thank you to the Artisan Asylum for giving us the opportunity, and Lars for helping us get this all together, and
Thanks, Lars.
supporting us throughout the process.
All right, good. Well, there are no more questions. Any more questions over there on YouTube Live? Is this a wrap? How are we doing?
Yeah, I don't see any more questions in the Zoom, so if there's no more on YouTube.
Okay. So that's a wrap. Thanks, everyone. This was exciting. We will have our second, let me come over here. We'll have our second artist in residence, a young artist, Ken. Do you remember the last name? Crestwell, right? Ken Crestwell is a painter in the Alston-Brighton region. She will be building a human scale nest in here. You know, COVID, we've all had to adapt to being isolated in different ways. And Ken's human scale nest is going to be sort of a way to encapsulate that experience for her, how her bedroom really sort of became this naturalistic nest for her over this 8-month period of social isolation that we've had. So looking forward to welcoming Ken on Monday. I can't believe you guys have put 1,000 hours or more into this. And now it's going to come down in 48 hours. Like talk about Buddhist art or something like that, right? Build it and then bring it down. But thank you. You guys have done a wonderful job. That's a wrap. Thanks, everyone.
Awesome. Thanks, guys.
Thank you very much.
Thanks for tuning in.